Assalamualaikum and good morning. So today I will teach you first order system, which is part of the chapter number 4. Okay, we are still in the E-micro course session. Okay, so in chapter number 4 there are actually several important parts. First we will see about the first order system. After the first order system we will see about the second order system. Next we will discuss about the Routh-Hurwitz criterion, and final part is the steady state error. Okay, so this figure shows the output response C of t. As you always know, before this we deal on how to develop the transfer function C of S over R of S. So now is the response of C of t, okay, when R of S is a unit step. Okay, so basically in this chapter 4 we will discuss about this output response C of t. Okay, and in the control system theory, this output response is divided into two parts. Okay, the first part is the transient response. Second part is the steady state response. Okay, so meaning that I can divide these signals or this output response into two parts. So the transient part is according to this one, okay, and the steady state part is according to this one. All right. So there are two parts of C of t. Okay, let's see the detail or the definition of the transient response. It is from initial state to the final state, and the purpose of a control system is to provide a signal or the output according to the desired response. Meanwhile, the steady state response is the manner in which the system output behaves as t approach to the infinity. Okay, so that is basically what you will learn in this chapter number 4. And in this figure also you can see several symbols here, TR, okay, TP, and also TS. Okay, so this symbol you will see later on in the next slide, okay, the detail, and maybe you will also see again this slide when you want to understand what is TR, TP, and TS. Okay. Next, also the definitions of transient and also steady state response. So the time response in the output response can be divided, like I said, consists of the transient response plus the steady state response. So the transient response goes from the initial state to the final state, and the steady state response is the system output behave as the approach to the infinity. Okay, so this is the general equation of the output that relates or that consists of two terms, transient part and also the steady state part. Okay, and this is one example of the equation of output response, which is, I think, it is first order systems. Okay, let's go to the first order system. So this figure shows the block diagram of the first order system. So the system here means this system. Okay, it is a first order system. All right. So let test signal is a step function. Okay, as you know before, this step function is a unit step function u of t, and I hope you know how to draw this unit step function. And if you convert this unit step function, you will convert to Laplace. I mean, you will get this R of S equals to 1 over S. Okay, next. Okay, so next if we obtain the final closed-loop transfer function of the previous block diagram, we will get C of S over R of S equals to 1 over tau S plus 1, where this transfer function is a first-order system without zeros. And next, we give a step input R of S equals to 1 over S. We can analyze the system output C of S as follows, where C of S equals to this one multiplied with the R of S, and we know that R of S is 1 over S, and we do the partial fraction to obtain this equation. Next, from the previous equation, we take the inverse Laplace to obtain a C of t. Okay, this is the important characteristic of the first order system, where we have this tau, right? After you do the inverse Laplace. Okay, this tau is basically a time constant which is equals to 1 over a. Okay, I repeat, the time constant tau is equals to 1 over a. Meaning that if t equals to tau, the step response, so the step response is C of t equals to 0.63, where it is equals to basically 1 minus 0.37. Okay, let's go through the detail of the time constant. Okay, 1 over a is referred to as the time constant of the response, and the time constant is the time for e minus at to decay to 37% of its initial value. In other words, the time constant is the time it takes for the step response to rise to 63% of its initial value. So I will recommend that you just remember this sentence. The time constant is the time it takes for the step response to rise to 63% of its initial value. Okay, because of this, the time constant is used to measure how fast a system can respond. Okay, when the time constant has a unit second, and the parameter a is also known as the exponential frequency. Okay, so the previous statement can be visualized using these figures, meaning that at t equals to time constant tau, you will get the value of 0.63k at the y-axis, where k is the final value. Okay. All right. You also can find the same things here at, for example, at 1 over a, where we know that 1 over a is tau, you will get 63% of the final value here. Okay, so this is basically the characteristic or the response of the first order system. Right. So besides that, we also have a TR and also TS. So what is TR? TR is a rise time, which is measured from 0.1 or 10% of the final value and 90% of the final value. Okay, 10% of the final value to the 90% of the final value. So there is a TR or rise time. And another parameter is a TS, which is a settling time. Okay, the detail will be explained later on. Okay, so this is the clear definition of the rise time and also the settling time. So for the first order system, you need to know these three characteristics or the three parameters. The first one, the time constants, tau, where tau equals to 1 over a. The second term is a rise time, TR, where TR is rise time, which is depend as the time taken for the step response to go from 10% to 90% of its final value. And TR is solving for the difference of C of t equals to 0.9 and C of t equals to 0.1. And other formulas you can use this one, TR equals to 2.2 divided by A. And next is settling time, TS, defined as the settling time, TS, to be the time taken for the step response to come within 2% of its final value of the step response. And other formula you can use this one, TS equals to 4 over A. Okay, as an exercise, yeah, you can try to find or calculate the time constant tau or Tc, the settling time Ts, and the rest time Tr for the given G of S. Okay, yeah, it is a simple question. The solution is that first you need to convert the given transfer function to the standard transfer function of the first order system as shown here. Okay, so meaning that if you refer to the given G of S, you can say that tau is basically 1 over 50. Alright, so then after you know what is tau, which is 1 over 50, meaning that A is equals to 50. After you know A equals to 50, you can calculate the time constant. So you know that tau is 1 over 50. And next you can calculate the TS. So TS equals to 4 over 50. And then you can calculate the rest time, where TR equals to 2.2 over 50. Alright. So I think that's all for the first order system. And next, this exercise 2 you also can try. This one is not using the formula, but using the analysis from the given figure. Okay, so if you understand, for example, Tc, which is the time constant, should be taken when the amplitude is 63%. So you need to calculate where is a 63% from the final value. After that, you can project, for example, let's say this is a 63%, you can project to this response and then go downward to the time. Okay, then you can find what is a Tc or time constant. And next for Tr, yeah, if you go for the definition 10% to 90%, okay, 10% to 90%, this is just a rough estimation. Okay, you can, yeah, estimate the TR. Okay, and same goes to TS. If you understand the definition of TS, which is 2%, okay, 2% from the final value, then you can find the TS. Okay, so I think that's all for the first order system lecture. Thank you very much.